In this video, we will start our last unit, and that is Chapter 21. Now, in Chapter 21, we talk a lot about nuclear chemistry, and I want to kind of preface this chapter by saying that we're not going to talk about every single thing that is in this chapter. Instead, we're going to kind of take a highlight approach to this and look at kind of the basics of nuclear chemistry and what kinds of things we look to achieve in nuclear chemistry and understand about nuclei and how they're put together. And if you want a little bit more of an intense look, we'll talk about that more when we get into general chemistry too. But for right now, it's just kind of a highlight of some of the basics. And so in that vein, we need to start and talk about radioactivity, because radioactivity is really at the heart of why we study nuclear chemistry in the first place. And so, nuclear chemistry as a whole, as a field, is the study of reactions that involve changes of nuclei. So, you might have recalled one of our fundamental ideas, one of the key attributes of Dalton's atomic theory, is that atoms are atoms, and we cannot change from one type of atom to another type of atom in a chemical reaction. And that is still true. However, Dalton's atomic theory had no way of knowing anything about the idea of nuclear decays, that is, radioactivity caused by unstable nuclei breaking down and forming new nuclei that are more stable. And so radioactivity had been well known starting in the early 1900s, late 1800s. Becquerel, Rutherford, the Curies, they all used radioactive materials to do different kinds of um, science, to do different types of discovery. But it really wasn't truly known until um, more deeply into the nuclear age, what was happening, as would be the case of Becquerel and the Curies. Radioactivity is going to play a big part in the fact that they die at an early age, and have their quality of life really stripped away from them because of their prolonged exposure to radioactive materials. Now, along with the idea of radioactivity is the idea that there is such a thing as nuclear stability. And nuclear stability comes from the idea that when I put those protons together in that nucleus, those protons are all positively charged. They're going to repel each other. And how much they repel each other, how difficult it is to keep that nucleus together, is met by a variety of different factors. Now, one of the factors we do know plays a role is neutrons themselves. Neutrons do play a role in stabilizing the nucleus. And what we can actually look at is the ratio of neutrons to protons is actually a really key factor in terms of predicting whether or not a nucleus is going to be stable. We can predict this stability using something called the belt or band of stability. And so what the belt of stability is if I were to take and graph on a normal kind of axis, if I were to graph on the vertical axis here, number of neutrons, and on the horizontal axis here, number of protons, I could plot through a series of different points and dots and whatever, all of the known nuclei in the world. What the belt of stability says is, okay, these are the ones that we know happen to be stable, and these other ones that exist, and we know exist, are not. And what we'll notice is that, I'll show you the belt of stability on the next slide, is that the band of stability is following a pretty predictable ratio of protons and neutrons. In fact, for light elements, that is elements where we have atomic number of less than 20, what we'll see is that that ratio of nuclei is about 1 to 1, give or take a proton or neutron either direction. And if you look on the periodic table, that is shown in the average masses. Remember, the average mass is the weighted average of all the different isotopes and multiplied by their abundances. So if you look, for example, helium, its molar mass is 4. That's 2 protons and 2 neutrons. You look at beryllium, its molar mass is 9, 4 protons, 5 neutrons. You look at calcium, molar mass of 40, 20 protons, 20 neutrons. So for the light elements, we see this ratio kind of holding up. And again, give or take 1 proton or neutron either way. Once we get beyond that, we start to see that the bigger nuclei are going to require more in the way of neutrons. And so as we get up to the heavier elements, we're going to see about a 1.5 to 1 ratio. So take just for example, iodine. Iodine, its average molar mass is 127. It has 53 protons, 74 neutrons. So take that, add about 1.5, and you get that ratio. Things that are unstable fall into one of 2 categories. They are either neutron rich, which means they're unstable for having too many neutrons, or they are neutron poor, which means they're unstable for having too many protons. And so when we look at the band of stability, we can see all of these black dots are stable known isotopes, nuclei, of a given element. And we can see that up until we hit about number 20 here, I'm going to draw in our line here to show where n equals 20 crosses up. So we can see up until this point, it's pretty much right on that 1-to-1 line. This red line is a 1-to-1 ratio. Once we get at 20, we see it starting to bend up until we finally get to bismuth. And bismuth, which is the last known stable isotope of any element, has a proton to neutron ratio, a neutron to proton ratio rather, of 1.52. So here's iodine, as I mentioned before, it's about 1.4 to 1. Here's bismuth at 1.5 to 1. So all of these yellow dots represent isotopes that we know exist, but we also know are unstable. And so depending upon position, we can look at, okay, any of these ones here, these are actually your neutron poor. They've got too many protons, not enough neutrons. And then any of these ones that are up here, which there are fewer of them, these are your neutron rich. And there are different modes of decay that get associated with each of these. But overall, all of these unstable ones are going to undergo some kind of a nuclear reaction to get to the band of stability again. It's just a matter of what it does. So we're going to close out this video by asking a really important question that might have come across your mind and you didn't know how to answer at one point in time. What holds the nucleus together? We've mentioned before, we've got all these protons all together in this really close and compact space. Why doesn't that repulsive force, all of those protons jam-packed together, why doesn't the nucleus just fly apart, disintegrate, go back to a clump of protons and a clump of neutrons? And the answer to that is a concept that you probably haven't heard before. It's the idea of something called strong nuclear force. Now, strong nuclear force is one of the fundamental forces of nature. And ultimately, it is what is responsible for binding together any subatomic particle, especially those subatomic particles inside of the nucleus. Now, we can measure, or at least estimate, the strong nuclear force associated with a nucleus by calculating something called the nuclear binding energy, or simply binding energy. Now, the binding energy is what holds a nucleus together, and we can calculate it by understanding that the binding energy associated with a particular substance is equal to its mass defect multiplied by the speed of light squared. Now, if this equation sounds familiar to you, it should. It's got another more common E is equal to mc squared, the classic Einsteinian equation. Now, this mass defect is the important part of this. This is really what causes this to work. And it's the difference between the mass of the nucleus itself and the masses of the nucleons, the protons and neutrons combined together that make it up. And so to calculate that, let's do a quick look at an example. I've got helium-4. It's got 2 protons, it's got 2 neutrons. The mass of each of those is here. Let's take a moment and calculate what the mass total is and compare that to the mass of the nucleus itself. So I've already taken the liberty of calculating the mass of 2 protons and 2 neutrons just by multiplying each of these by 2. Now, the total mass of the nucleons would be 3.346 times 10 to the negative 27th plus 3.350 times 10 to the negative 27th, which would be 3.696 times 10 to the, or excuse me, 6.696. 6.696 times 10 to the negative 27th kilograms. And if we compare that to the mass of a AMU in kilograms, which is 1.661 times 10 to the negative 24th kilogram, or grams, which would be 10 to the negative 27 kilograms per AMU, I get 6.642 times 10 to the negative 27th kilograms And so if I compare these, 6.696 minus 6.642, (6.696 minus 6.642 times 10 to the negative 27th, we get a mass defect of 5.4 times 10 to the negative 29th kilograms. And so that little bit of mass, when we multiply it by the speed of light squared, that's going to be our overall binding energy. And that is what's going to hold together that nucleus. So that's it for this video. We're going to look at next time the types of radioactive decay that actually occur and how we can measure some of those decays. Have a good day.